Okay, so let's get started. So today we are going to continue the discussion we started last time. So if you remember, last class we started talking about, oh, all right, sorry. I'm going to share this again. Okay, there we go. So last time we were talking about clock synchronization. I described multiple clock synchronization algorithms, and towards the end of the class, I introduced this notion of Lamport's clock or logical clocks, which get away from the problem of having to synchronize the clocks on different machines, but they allow you to create a time stamping mechanism which gives us certain properties. The properties were defined by the happened before relationship, where we said if you can order events either based on their execution order or based on message exchange between processes, then we have a timestamping mechanism that allows us to add timestamps to these events that respect the ordering that we want. Okay? And one of the issues there was that the happened before relationship allowed us one direction implication, which means if two events happened in a certain order, Lamport's clock algorithm assigns them clock values in that order, because the one is greater than the other. But the reverse was not true. So now we are going to generalize that today, talk about a general version of this concept, which we will call vector clocks, and we'll see how we can get implications that go in both directions. Okay? But before we do that, I just wanted to give you a very simple approach that can take the Lamport's clock algorithm, which gives us partial ordering of events, and construct that into total ordering. Okay? And the way we can do this is essentially append the process ID to the Lamport's clock value. So here is process number 1, process number 2, process number 3. The integer values are the Lamport's clock values. Okay? And then you just append as of after the decimal the process ID, and process IDs are assumed to be unique. Okay, that automatically constructs an order that's arbitrary. Okay, but we will assume that that's essentially the order of events. So this is going to respect Lamport's clock values, but also by assigning these process IDs to Lamport's clock values, you just construct that partial order into a total order. So now you can say that 1.1, event 1.1 and 1.2, although they are technically not ordered as per Lamport's clock, they are concurrent events. You'll see that there is no message exchange. We will just, for the purpose of total ordering, assign an arbitrary order between them. Okay? This is just designed by us. There's not a real ordering there, but to construct a total ordering, this is what we will do. We'll assign process IDs that automatically breaks ties. If there are two events, both got, let's say, Lamport's clock value of 1, which is what happened to event A and event E here. By attaching the process ID, this clock value has become 1.1, not 1 anymore. That became 1.2. Now there is an ordering, okay, which is arbitrarily designed. It's sort of a tiebreaker that we assign to get a total ordering from this event. And so whenever you use Lamport's clocks, you only get partial ordering. And then if you use this approach, you can convert that partial ordering into some sort of a total ordering. And that is something that then you can use to make some determination with respect to timestamps and so on. Okay? Note that for concurrent events, this total ordering just gives you some arbitrary order between events. That's not a real order. Okay? If you had real timestamps or physical timestamp, that ordering may be different. But for Lamport's clocks, this is good enough. Okay? All right. The other thing I want to mention is where would you use these types of approaches? I explained the Lamport's clock in an abstract setting. I did not give any specific use cases. Okay? Here is one example. The example is one where you have a bank database. Okay? And the database is replicated for reasons of security and the fact that this is important information that the bank cannot afford to lose their customer data. So you see that the database is replicated. This database is accepting queries from customers. This could be account updates or other types of queries. Okay? And you have two users here. You will see that there are two users that they are sending queries. Queries are actually sent to both replicas. That's why you see that the request from this user here is actually sent to both replicas, and the request from the other user, which is shown as dotted arrows, is also going to both replicas. Okay? Now, some users might be closer to some replicas than the other. So when they send these queries, their queries might arrive in two different order in this database. So in particular, you will see that the example is showing that the left user's query arrives first, and because the right user is much further away, that query takes longer to propagate and arrives second. So here you get them in one order, but the order is reversed at the other database. Okay? The other user's query, which arrives faster because the user is closer, and then this the first user's query arrives later. Okay? So queries that are sent arrive in two different orders at the two different databases. If these queries were making updates, they can actually result in errors. Okay? So here update 1 is performed before update 2. Here update 2 is performed before update 1. So you don't really want this. Okay? For the database to stay consistent, all operations have to be performed in the same order on these databases. Otherwise, you might actually have inconsistencies between these two. For example, in one case, you might be withdrawing money, okay? And the second operation, which is shown as user operation, might be adding interest based on how much amount is remaining or something like that. And if that interest process is actually operating on two different account balances, because in one case happened before the withdrawal, in one case after, you will get inconsistent result. Okay? So what you want to do is avoid this type of problems. You don't want databases to be processing requests in two different orders. There, you should do them in the same order to keep them consistent and synchronized. So this is a good case for using Lamport's clocks and giving a total ordering. So these messages can actually come with clock values. You can use events, in this case are queries that are coming into system. You use Lamport's clock values, and then you assign a total ordering based on what I said earlier. Okay? And that ordering is respected by all databases. So once you have this total ordering, all messages will actually be processed in that total order. So that means that even though the messages are being received in two different orders, they will be processed in the same order, because the Lamport's clock value will reorder them, okay, based on that assigned timestamp. The timestamps will always give you a numerical ordering, and you just process them in that order. That will ensure that regardless of how it is received, it's always processed in the same consistent manner. This is one example of where you might use things like Lamport's clocks to get total ordering and ensure consistency across replicated databases. Okay? We'll come back to some of this when we talk about consistency and so on later on. So just a very simple example to explain to you why these kinds of techniques are important and useful. Okay? All right. So let me now talk about vector clocks and the need for vector clocks. So last time, as I said, we talked about logical clocks or Lamport's clocks. They had the following property. Okay? If you have two events in a distributed system, A and B, and you knew that A happened before B, either because they are executed, those are events that executed in that order, or A is the send, B is the receive. Send always happens before the receive, or there is some transitive relationship. So, but you know that A has happened before B, then what Lamport's algorithm did, it assigned clock values to these events, and it always ensured that the clock value of A is strictly less than the clock value of B, because A has happened before B. A gets a lower timestamp than B. That's what it's saying. Okay? So this is what Lamport's clock gives us. If you have two events and A has happened before B, it guarantees you that the timestamp the algorithm assigns to A will always be less than B. Okay? Now, the reverse is not true. Okay? Lamport's clock does not tell you that if clock value of A is less than clock value of B, then that actually implies that A has happened before B. Okay? We actually want that reverse property, because you want to be able to take timestamps and compare them, okay, and reason about them. Saying if one timestamp is less than the other timestamp, you should be able to say, okay, this has a lower timestamp, so this event has happened before this other event. So what we actually want is the reverse property, which Lamport's clock did not give us. Okay, it gave us one direction. So in other words, the implication has to be bidirectional, but we don't yet have that. Okay, so we need to now come up with an algorithm that improves on Lamport's algorithm and gives us the property that goes both ways. Okay, that's going to get us to vector clocks. But to get there, I want to define this term causality. Right? And causality in our case will mean if A has happened before B, then event A is somehow causally related to B, meaning that there is some causal relationship that involves sending and receiving messages and execution on local processes that allow us to say that A and B are causally related events. Okay? If these two events are independent, then we say there's no causal relationship between them. They're concurrent events. Okay? And we'll come back to causality in a little bit. But when you have causality, you can actually have systems that use this causal relationship between events to give you other properties. So for example, causal delivery says if there are two messages M and N, and the send of the first message happened before the send of the second message, then the receipt or the delivery also has to be in that order, meaning that if one was sent before the other, they should be delivered in that order. So that means it's causal delivery. You don't get reordering in the network, okay, because the sends are ordered. So that's an example of a system that can actually give you that property. Doesn't mean every system gives us that property, but you can use causality to impose certain ordering of relationship. Okay? But we'll come back to that. For now, our problem is to actually come up with a timestamping mechanism that says that if timestamp of A is less than timestamp of B, then A should have causally preceded B. Okay? A has happened before B and hence causally preceded. So we want to be able to take two timestamps, okay, compare them, and that should guarantee you that if the timestamps are ordered, the events are also ordered. Okay? All right. So how are we going to do this? The algorithm is a fairly straightforward extension of Lamport's clock algorithm. Okay? In Lamport's clock, the clock value was a single integer. Okay? At each event, you just incremented the integer. Okay? And then when you sent the message, you included that integer with the message, and at the other end, you compared them, took the max, and you added one. That's all you did with Lamport's clock. Okay? We are going to do something very similar, but in this case, our clock value is no longer an integer, it's a vector. Okay? It's a vector of integers. Okay? So there's one integer per process in the system that communicate. If there are n processes, okay, this is an n vector with n elements in it, or an array with n elements in it. Okay? For process I, the ith element of the vector is its local clock. That's the same as the Lamport's clock. Okay? But you also keep track, each process now not only keeps track of its own clock, because you have a vector, you are keeping track somehow of other clocks as well. That's what the vector is for. Okay? But beyond that, the algorithm is very straightforward. It's actually the same. Okay? Whenever a local event occurs, okay, at process I, you are going to increment the ith element of your vector. Okay? This is like incrementing your local clock. So if there are three processes, you have vector with three integers. Okay? If there's an event on process 2, it will increment the second element of that vector. Okay? And I'm going to show you an example of this. Okay? And then when you send the message, just like you did in Lamport's clock, you send your clock, okay, which is the entire vector. Okay? Previously, you sent one integer. Now you sent a vector. Okay? And when you receive the message, okay, you are going to do the same thing. You are going to take the max of the vector that came with the message and your own vector clock, and you are going to essentially take the max of the two. Max of the two essentially means you are going to compare element by element of the vector and take the max of each element. Okay? So on the receipt of a message, you take the max of the two vectors, and you also do the j. If you are process j, you also increment your local clock value, which is the jth element of that vector, which was exactly what we did previously. You took max of the 2 plus 1. You take max of the 2 vector, but the plus 1 is only for your local jth entry. Okay? And that's it. Okay? That's all we are going to do. So it looks very similar as before. Okay? You are going to keep now a vector of integers. For local events, you increment your ith element in that vector. Okay? When you send messages, you include the vector. When you receive a message, you take the max of your vector and the one that came with the message, and you add 1 to your jth element. Then that's all you do. Okay? So let's now take an example, and then we'll try to understand why we got this property. If you compare these vectors and timestamp of A is less than timestamp of B, now you can claim just by looking at the timestamp that A has happened before B or A causally precedes. Okay? So let's do an example first. Okay? I hand drew this because I didn't want to draw it on the board for students who are online, so I put this here. But here are three processes, okay? P1, P2, P3. So our vector clock is an array of three integers. Okay? All clocks start with 0, 0, 0. They all start with 0. Okay? P1 is process 1, this is process 2, process 3. Whenever there are local elements, you increment the local the element of that vector. So when P1 will go from 1, 0, 0. It went from 0, 0, 0 to 1, 0, 0. Next, you'll go to 2, 0, 0, and so on. Okay? At P2, you will increment the second element. So whenever there's a local event, you go from 0, 0, 0 to 0, 1, 0, and so on. Here, you will go from 0, 0, 1, 0, 0, 2. So increment the third element. Okay? So the local event, you just take your local clock value within that vector. Okay? Now, here is a message M1 that's gone from P1 to P2. Okay? It is going to include this vector as part of the message. So 200 is going to go here. Okay? Now, when the message is received here, you are going to take the max of the vector that came and max of your vector, which is 0, 2, 0. Okay? So you'll take the max. So you'll take pairwise max. So this, you'll compare the first element and say the max of 2 and 0 is 2. You compare the second one, which is 0 and 2 is 2. But then since your process 2, you also increment it by 1. So this became 3. And then you take the max of the third one, which is 0. So now you got a clock value of 230. Okay? And then the next element here will just make it 240 and 250 and so on. Okay? And you do the same thing here. You'll see that there's a message that went here to 240. You take max of 240,004, and then you actually, 250 and 004, and then you add 1 to the third element. So that gives you 255, and so on. Okay? Is this clear? What I did was just a numerical example. So like in vector clocks, or right in logical clock, everything we said about happened before relationship is true. For local events, those events are executing sequentially. So an event that executed later has happened after the one that happened before. Okay? And send and receive are always ordered. Send of a message always happens before the receipt. Okay? And this is transitive. So all the events before the send and all the events after the receive get ordered based on transitive property. Exactly what I said before. Okay? Last time I said the same thing. Okay? Now you can look at the clock values and you will see that that's actually true of the clock values as well. So if I take a event before the send. So here are some examples. Okay? Let's compare A and B. The event A is in process 1, event B is in process 2. The first question is, are events A and B ordered? Can you say something about which event has happened before which event for A and B? Okay? A has to be before B because A is before the send is before the receive is before B. So by transitive property, A has happened before B. Okay? Look at the clock values, 100, 240. You say which vector is bigger? Okay? Okay? You see that 240 is greater than 100. So you actually have a timestamp. It's not a proof, but you're seeing that because 240 is greater than 100, and that's actually respecting the fact that A and B are actually ordered that way. Okay? Now look at A and C, okay, which is now a third event and the third process here, okay, which is 256. First thing is you will realize that there's no message that goes directly from process P1 to P3. Okay? Yet the question I would ask is, are A and C ordered or not, even though there's no direct message exchange. Okay? Okay, there's transitive property because A is before this send, that send is before this receive is before that send, which is before this receive, and then that's before that. Okay, so transitive property still holds. You don't need direct messages. Messages that go from one process to another also cause events across processes to get ordered, even though those two processes are not even communicating directly. Okay, so that's clear. Now A has happened before C. You will see that the clock values also tell you that this is 100, that's 256. The vector for C is greater than vector for A. Okay. All right. So far that's not much very interesting, but now let's look at A and D. Okay, A is in process P1, D is in process P2. Are these ordered? First of all, there's no message exchange between P1 and P2 that sits between A and D, right? Because A is before the send, B is before the receive. You can't really say anything. Okay, so these two events are called concurrent events. You cannot order them because there's no message exchange that allows us to order them. There's no transitive property here between these two processes that allows us to order them. Okay, so A and B are actually not ordered. They are concurrent events. So now let's look at the timestamp and see what they tell us. Okay, so timestamp of A 100, timestamp of D 020. Okay, how do you arrange these vectors? One greater than the other? Yes, no. One is greater. Whose? D is bigger. Okay. So first question is, you should ask, what do you mean by one vector is greater than the other? I never defined what greater than means for a vector. Okay. You know what greater than means for integer, but what does greater than mean for a vector? Okay. I actually didn't define that. So let me first define it and I will re-ask that question. Okay. Vector for A is less than vector for B, or let's say vector B is greater than vector A if every element of B, okay, is greater than or equal to an element of A, and there's one element that's strictly greater than. Is that clear what I just said? So let's just draw this. So you have two vectors, okay? Let's say A1, A2, A3, and B1, B2, B3. Okay? We'll say that B is greater than A if every element here is greater than or equal to. It must be at least equal to, if not strictly greater than, all the elements here. There's at least one element that's strictly greater than. Okay? Which means that all the elements of B have to be greater than or equal to here, with one element actually greater than. That's what we mean by greater than property for, or this is how you compare two vectors in our, based on our definition. Okay, now let's go back to this 100 and 020. What does this tell us? Is one greater than the other? No. Okay, so these, you can't compare them because the first element here is greater than the first element there, but the second element is less than. So in one case, some elements are greater, some elements are less than. So neither is A greater than B, nor is B greater than A. So these two vectors are not comparable. Okay? And that is precisely what we want, because if they were comparable, then those two events should have been ordered. That's what we said, right? And we just said A and B are not ordered, and you will see that the vector timestamps now do not give us an ordering. They actually conflict. They say A and B cannot be ordered because the vectors cannot be compared. Okay? So this is how you will see that vector clocks have now given us the reverse property. When events are concurrent, the vector values become incomparable. You cannot order them. But when events are ordered, you can strictly order them. Okay? So this always allows you to now compare the timestamp, and just by looking at the timestamp, if the vectors can be ordered, you can now say that one event has happened before another event. If the vectors cannot be ordered, you can just say these events are concurrent. Okay? And you can now, I mean, that's not a proof, but I'm just giving you examples. You can see why that is the case now. Okay? If it was logical clocks, these were integers. You could not say this because these A and B would just be two integers. Okay? They're always comparable by definition because those are integers, right? And so just because one is greater than the other or not, you can't say. In this case, those vectors actually become not comparable. Is that clear what I'm saying here? Okay. All right. So that's vector clocks for three processes, and you can do the other examples. You will see the same thing. When you have the happened before relationship, you will see that the vectors are comparable, otherwise they are not. Okay. So this is giving us the same partial ordering we had, but the vector clock values also represent that, not just the picture, but they're also represented in the timestamps. Okay, any questions here? Or I move on. Okay. So this is another way by which you can do timestamping, and you can compare events based on the timestamps, and you can reason about them just by looking at the timestamp. Okay, so now we have the implication going both ways. Is A happened before B, vector clock of A will be less than vector clock of B, and the reverse is also true. The vector clock of A is less than vector clock of B. A has happened before B. And there's also another way of saying if the vector clocks are not comparable, you cannot order the event, they're concurrent events. Okay. All right. So here is a use for this kind of vector clock. So you can actually enforce causal delivery that I was just telling you, which is that if two messages were sent in a certain order, you can actually then deliver them in a certain order as well. Okay. So here's an example. You are now sending messages here from across these processes. So P0 is sent, in this case, it multicast a message, which means the message goes to both of the others, right? So you say message M is sent to both P1 and P2, and P1 is sending a message that goes to the other two. Okay. Now, you can ask, are these two messages M and M star ordered? Okay. And you will see that this is the send of the first message. Okay. And P1, there's a receipt of that first message, and then the send of the second message happened after the receipt. Okay. So these two sends have become ordered events. Okay. The send of the first message has happened before the send of the second message. Okay. Now, if you want to impose a property called causal delivery, not every protocol will impose it, but let's say you want to have causal delivery. That means if messages are sent in a certain order, they should also be received in the same order. Okay. The message that was sent first must be received first. Okay. So essentially what that means is M has to be always be received before M star at all processes. Okay. So now here is a case where this M here actually arrives, so not M. The M star probably has a lower latency to the third process, so that message actually arrived at P2 while the first message is still on its way. Okay. So you see that M arrived here. Okay. And if you had just delivered it, that would have violated our causal delivery because the second message has arrived at the third process before the first one. The first one is still taking its time. So you will see here, this process actually did not take delivery of this message. It basically waited until the first message was received and then delivered the second message. So it held it in a buffer, delayed it, and then delivered it after the first message was actually received. Okay? This is called causal delivery. Okay? The reason you can do this is because you can actually look at the vector timestamps and see that there are some messages in transit that have not yet been delivered. Okay? How do you see this? You can actually do this using vector clocks. You'll see that this vector clock value here is 100. Okay? This one has 110. Okay? So this one, the message 110 actually arrives at process P2. P2 says that because the first element of the vector is 1, process P1 has sent a message. That's not yet, but I have not seen it yet. Okay? Because you can see that because that clock value got incremented here. And then if then that's received here, you know that there is at least one message that P0 has sent that you haven't even received. So you can delay that in your buffer, wait for that message to show up, and then deliver it. So you can look at vector clock values and reason about what has happened in other processes based on what they're telling you. So they tell you how many events have occurred at other processes. Okay, that's the clock value is telling you that. Okay. But the high level thing you want to understand here is because these two sends are ordered, the receipt has to be ordered, and if they arrive out of order, you can hold the messages in a buffer, delay its delivery, and deliver them in the same order. So you will see that the messages are always received in the same order at all processes. Okay, that's the high level thing to take in mind. That's what vector clocks now allow us to do. Yes. Question is, are you not implementing the timestamp when there is a receive? So this is a picture from the book. So what it has a small variant of what I showed you. What they are doing is they are just taking the max of the two. The algorithm I said also has to increment this by 1, right? So if you implement this algorithm strictly in this case, this would have actually become 120 because this is a second event. Okay? They didn't do that. They just took the max. It works in either case, but yes, if you take what I showed you, this should have a 120 here, not 110. But that doesn't matter. It gives you the same result in the end. It's a good question. Any other questions here? Okay, so that's vector clocks. I am going to switch gears and talk about a different problem in distributed systems, which is called the global state, capturing the global state of a distributed system. Okay? I'll define what it is, but then I'll also explain why this matters, because our definition is somewhat abstract, so you may not get an appreciation of why this is even important. Okay? But let me define what this term means. Okay? That's a global state of a distributed system means is the local state of each process, and the local state just could be memory state. So the global state of a distributed system would be local state, which is the memory contents of each process and all the messages that across the system that have been sent but not received, which means all the messages in transit. Okay? So this is our definition of global state. The global state of a distributed system, you can think of it as the memory state of all the processes and all the messages, all the TCP/IP messages or RPC messages that are in transit, which means they have been sent but not yet received. They're somewhere on the network or sitting in some queue somewhere. Okay? That's what we mean by global state. Okay? Now, we'll say, well, why does this actually matter? What do we do with knowing what the global state is? So global state of the system is important for reasons of failure recovery. Okay? And here's the example I'll give you. Okay? So let's assume that you are running some long-running job, bad job. It could be, it's a distributed job, not a single process job. Let's say it's machine learning training or some parallel simulation. Okay? These run on a cluster. Okay? So now, let's say your job runs for 6 hours. Okay? Let's say there are 5 processes in your job. There are 5 worker nodes or 5 processes. They are running on different machines. They ran for 5 hours, and one of the processes crashed. Okay? Because there are 5 of them, one crashed, the others are still running. Okay? Now, your job is not going to produce an end result because one of the components of your ML training or your simulation has failed. Okay? What will you do in this case? What's the simplest thing you can do? Yes.
Restart that part on another machine.
Okay. Restart that part. Okay, you can restart that part, but if you restart that part arbitrarily, if they're communicating with one another while they're computing, okay, any messages that were sent after it crashed and before it restarted are all disappeared, right? So just restarting it blindly doesn't work, because you might start that process in an inconsistent state, because these are not processes that are independent. They do communicate, right? So the process crashed and other process sent it some request command, they will all disappear, and you'll restart it with some inconsistency. So the simplest thing you can do actually is to terminate all the other 4 and restart everything from scratch. That's the simplest thing you will do, right? So you just say something crashed, let's just restart from the beginning. That will work, but you wasted 6 hours of compute, right? Now, what was suggested here would have been nice, where you can restart the failed process and the failed process alone, but that's not going to give you consistent result, because the failed other processes have done some computation, they have moved ahead. This computation will start, it doesn't know where it failed. It might start from the beginning, you'll get some inconsistent result. Okay? So what you want to do in this cases is periodically you want to somehow save intermediate results or intermediate state. Okay? You can say every 1 hour you save whatever work you have done to disk. Okay? And then you compute further. Okay? And next hour you do the same thing, you save your results. Okay? Now if processes crash, you go back to the previous saved results, you load it up and you start from there. Okay? That means that all the work you've done is somehow saved in the form of intermediate state or results, because you kept it on disk. You don't have to go all the way back and restart. Okay? So now if a process crashes, you terminate all of them. You don't restart from the beginning. You go to the previous saved state. You say, this is what I saved 1 hour ago. I'm going to load that information and start from there. Okay? That's much better, because now you don't actually waste everything you've done. You're periodically, it's called checkpointing. You're periodically checkpointing. Okay? You're saving your work. Okay? So you don't actually have to go back from the beginning. Okay? So that's basically why you need to think about global state. Global state is just a way of saying, how do I checkpoint everything I know about these processes so I can restart them from this point. This is a checkpoint. Is that clear? What checkpointing means? Okay. It's not very different from, let's say you're editing a file in Word or something like that. You don't periodically save, okay, and your process crashes, you might lose all your edits. So when you edit in a browser, or not browser, edit in an editor, you do save your state every once in a while. Okay. Modern editors actually do auto save, so you don't even have to do this. They are saving for you in the background, but not all of them do. So you do have to save whatever changes you made, so you know it doesn't disappear. It's the same thing, but in a distributed system. Okay. So, but then the question is, what does it mean to actually save state? Okay. You have to do this in a consistent fashion. Okay. So this is where this clock synchronization comes in. Okay. If all the clocks on these processes were perfectly synchronized, say, okay, perfect synchronization, you could instruct the processes exactly at the beginning of each hour, pause computation. Okay. So everything is paused. Save all your work to disk, okay, restart computation. Okay, that will work because you are all synchronized. So you're saving state at exactly the same time, right? So then it's consistent. Okay, but as you well know, okay, we said there is no such thing as a perfect clock synchronization. All clock synchronization has errors in it, right? When we talked about NTP, I said this. So you cannot actually do this as a stop at the beginning of each hour and take a checkpoint, because all these clocks are slightly off from one another. Okay? Very small amount, but they're still off. They're not perfectly synchronized. So they will not all save state at the same time. They will save slightly off from one another, which may be some hundreds of milliseconds or tens of milliseconds, but they're still off. That can still cause inconsistencies. Okay? So you cannot, if you had a perfect world where all the clocks are synchronized, this would be a trivial problem. You would say stop at the same time t, save state, resume, okay, and you do this periodically, all set, all done. But we don't have a clock synchronization algorithm that's perfect, which, as I said, also is its fancy way of saying that is there is no global clock, there's no perfect synchronization. So now what are we going to do? How are we going to save this state? Okay. So I'm going to tell you an algorithm to do this that's actually nice. But before I do that, I want to show you why it is actually problematic if you save state at slightly different points in time. You might say, what's wrong if they're off by 10 milliseconds? Right? Clocks are not perfectly synchronized. They may be off by 10, 20 milliseconds. What's the problem? Why is that bad? Even if they're slightly off, they're just saving state at more or less at the same time. Can this cause problems? So here's an example to show you why there is a problem. Okay? So here are three processes that are doing some computation. They send some messages back and forth as part of your distributed application. Now, if the clocks were perfectly synchronized, okay, you would say stop at this time, which is a vertical line through this, that's time. So x-axis is time. So the time will be completely aligned. It will say stop at this time t, okay, and save state. Okay. Now, because the clocks are slightly off, time t is somewhat different on these three processes. This is why this dotted line, okay, where it intersects is each of these processes on different machines is time t on that machine. Okay. And because the clocks are slightly off, time t, which is the same time on machines, is slightly different. One is a little faster, one is a little slower. So each of these processes is now pausing at a different time in real time because the clocks are slightly off and saving their state. Okay. That's what is going to happen if the clocks are not synchronized. Okay. Now, in some cases, that having these clocks off does not cause a problem. This is an example where having these clocks being a little off and saving that state at slightly different time causes no problems. And in some cases, it does. And here's an example where it does. Okay. Now, the technical way of saying this is the first example is what we'll call a consistent cut, which means that the state that you saved is consistent, the cut is consistent, and the cut just essentially means where does this dotted line intersect these processes, that is where they will save the state. Okay? So process P3 will stop at this time t, save state. Process P2 thinks that's time t, save state here. Process 3 saves state there. Okay? They're not exactly the same time t in real time because the clocks are off. But we'll say this one we will accept. This is consistent. This one we will not accept. This is not consistent. So what's the difference between these two examples that makes one of them consistent, the other not, even though in both cases the clocks are not synchronized? Okay? So here's the main thing that you want to keep in mind. Okay, you have that dotted line, that's your cut. Okay, that's the state that you saved on disk. Wherever the clock, wherever that dotted line intersect, that's the time at which you save state. Okay, now we will say that the cut is consistent, or that checkpoint is consistent, if all the sends and receives of messages are either to the left or to the right of the cut, and the only time a message actually crosses the dotted line, the send should be on the left and the receive should be on the right. Okay, so that means that all the sends and receives have happened before you saved state, or all the sends and receive are going to happen after they resume computation, which is M2. M1 is where the message was sent and received before you saved state. It's all done. M2 is a message that will be sent after you resume computation. It will be processed after you receive computation. Only time you are allowed to cross is if the send was actually before and the receive is after, which you will see M3 is actually crossing that dotted line, which means from P1's perspective, it's already sent M2 or M3, because it's saving its state after that point. So it's already sent. It will resume execution from this point on if you restart this process. Okay, it will never, but it will then M3 is something that's a message in transit in this case. So P2 has not actually processed this message, even though it has been sent, but we'll say this is consistent. Okay, because we'll also save the states of all messages in transit, and we'll save M3 in this case. Okay, but let's look at what is the problem here. Then you'll understand why this can be a problem if clocks are not synchronous. Okay, so in this case, M1 is to the left of the cut. Okay, so M1 has been received, sent and received before you even saved your state. You don't worry about it. M3 is after, to the right of it. Okay, that means that anything to do with M3 will be after these processes resume computation if you restart them. So we don't worry about that either. Okay, the problem is with M2. Okay, you will see that the receive of M2 is before the dotted line, but the send is after. Okay, that's just shown in the picture here, right? So I'm just telling you that the send is to the right, the receive is to the left. Okay, so then you say, what's the problem with this? Okay, so from P3's perspective, it has already processed this message before it saved the state. It saved the state at this point. The message has already been received and processed. Okay, now P2 saved its state at this point. Okay, now if you restart the entire computation, okay, you will start each of them where the dotted line intersects. That's the state you saved. Okay, so what is P2 going to do? It will start from this point. It will again compute and resend M2. Okay, P3 is going to start at this point. It's already processed M2, but it will get that message again. You'll get a duplicate message. Okay, if this was some database where the message is add $10 to this account, right? That message will come a second time. You will essentially process it again after you restart it, and now you are inconsistent because you process the same message twice. Is that clear what I just said? So you cannot, so if this problem never arises, if you have perfect clock synchronization, you would never have this. You are saving the state at the exact same time in real time. But clocks are not synchronized. You are slightly off. And if you do it this way, you have a problem. But in this case, you don't have a problem. Okay? So our job is now to come up with a simple algorithm that says clocks are not going to be synchronized. We cannot solve the clock synchronization problem. If you could solve it, then this problem is solved. We don't need to do anything. Right? But since we cannot solve the problem, how can we design an algorithm that is going to save state but guarantee you that it's always consistent? You'll never actually do it this way. You always do it this way. Is that clear? What I said? Okay. So that's the algorithm we want to look at. So that we'll talk about that in the next slide. But this is what we mean by saving the global state. You are going to save the memory state of each of the processes at this point, and you will save all the messages in transit, which means in this case, you will actually save a copy of M3 somewhere. Okay? When you restart, you will say M3 is a message in transit, not going to be resent. So you have to actually reproduce it and deliver it to P2 again, so it can process it. So you will save the memory state, and you will save all the messages in transit. In this case, there's only one message in transit, which is the one that crosses that cut. That's been sent but not received, so it's somewhere in transit. So you got to save that too. Okay, if you don't save it, then you have a problem again. You have a message that never got processed. Okay, so you neither want to have messages lost nor duplicate processed messages. Yes, question.
How is it possible that people send?
Okay. Question is about the consistent cut. Why is it that the sending is happening after and the receive is happening before? Is that the question? Is it possible, right? So let me explain what the cut here even means, right? Because the clocks are not synchronized, right? Let's say you tell all three processes, okay? At noon, pause computation, save your state. Okay, clocks are not synchronized, so noon for P1 is at this time, okay? Noon for P2 is at this time, and noon for P3 is at this time. Okay, so very simply, these three processes are going to pause at these three different times and simply save their state. Okay, that's all that we have done, or we have not done anything more. We just said at this time t, which we defined in this example to be noon, pause, save your state. And I showed you an example where the clocks are a little bit off. So P1, P2, P3 save their state at slightly different time. Now, as a result of doing this, you see what has actually happened, right? So in some sense, P2 has actually sent that message at this point in time, and it was received at this point in time. Okay? Now, it just so happened that P3 delayed taking its snapshot because its clock is running slow to a much later time, and as a result, its state has actually already processed M2. Okay? And P2 is probably running much faster, so it took its snapshot much before noon, so it hasn't even processed from this pictorial perspective M2. Okay? Because you're taking snapshot at slightly different points in time, between these two snapshots, you could have sent a message, processed it, but you actually have taken snapshots in an inconsistent manner. So that's what it is. It's not that there is something magic going on here. You just took snapshot at different times because your clocks are not synchronized and caused the problem. Your question is?
Not exactly at the process. That after 1 hour, that
Okay, I'm not following your question. You're saying take it after 1 hour? Yes. Yes.
that
Okay. Question is, if you're asking if you take the snapshot after every 1 hour, is that consistent, right? It is only consistent if the clocks are synchronized. Okay. What does 1 hour mean? 1 hour is some point in time, right? So you are going to say take it every 5 minutes. Okay, so you'll take it at 12, 12:05, 12:10. Every process is doing the same thing on its machine, but if the clocks are not off, you compare when they're taking the snapshot with real time, they're actually off. Right? Yes. Okay. Question is, if each process saved its own state, where is the messages in transit saved, right? So in this case, I'll show you the algorithm on the next slide. What you have to do is you have to not only save the memory state, but you also have to save the TCP/IP state, which is where the messages are queued somewhere. Either they're in the TCP/IP buffers on the sender, or they'll appear on the TCP/IP buffer at the receiver of some sort, right? So you have to essentially save your network state and your memory state. That's the short answer to this question. Okay? Yes. Okay. Question is, can you save M2 somewhere, and then when you save it, when you do it later, compare? That's your question, right? So you may have to, if you do that, you might have to save all the processes that have been received. This could have gone way back, and there could have been 10,000 messages that were sent. You don't know which one has actually crossed the cut, right? A better algorithm is, can you just do this to begin with and not have to worry about it, right? Okay, so question is, are you asking in consistent cut, there are many messages. So in a consistent cut, you only say messages that are going to cross the dotted line, because that's what we mean by a message in transit. The message that has been sent, but not yet received as far as the other process is concerned, somewhere in transit. It was sent before noon, but it's arriving after noon. That's what you should think. So somewhere in between, you took a snapshot, so it's in transit. You have a question there?
Their messages, if it's like a buffer period, and there's that, like, if you're like confident that they're somewhat synchronized, you avoid having like any messages sent in zone of like danger.
Yeah. So question is, can you instruct processes to save some of their network messages somewhere around the time of the cut. So you save some of them and then you can figure out if they are received or not. You could do that, but then you have the additional work of saying for all the messages you saved, which ones were processed, which ones shouldn't be processed. You added some extra work, right? So it's not that you cannot do that, but then you have to make sure that every process must receive the message only once and process it only once, every message that's sent. That's what you got to guarantee. If you save extra ones, you got to make sure that when you look at this buffer, which ones are the more relevant ones, which are the ones that are not being processed, right? Okay. So let me show you an algorithm to do this. Okay. It's called distributed snapshot algorithm. It's a algorithm that actually allows you to save your memory state and all the messages in transit. But let me give you intuitive example of what is actually happening, okay, so that you can get some sense of how this algorithm works. Okay. So it's called distributed snapshot, but my analogy is going to be like taking an actual snapshot or a picture. Okay. So let's say you have the sky, okay, that you can look at the sky and you can see that maybe there are some birds in the sky or there's some cloud in the sky, and you want to capture the state of the sky. Okay. So one way you can do this is you can take a photo of the sky. Okay. And the photo is your snapshot. That's captured the state of the sky. Okay. But assume that your camera does not capture the entire sky because it can only see a portion of the sky. The field of view of your camera is such that you can only take a picture of a part of the sky at any time because the sky is actually much bigger than what your camera can capture. Okay. So what are you going to do in this case? Okay. You can say, let me now take multiple pictures. I'll take a picture of this part of the sky, then I'll take a picture of this part, and I'm going to stitch them like a panorama, and that's my state of the sky. Okay. You can do that, okay, but you want to do this in a consistent manner. Okay. So what does consistency mean in this case? Okay. So let's assume that the sky is not static. There are some birds flying in the sky. Okay. So I take a picture here. Okay, let's say that there are some birds I captured, and I take a picture of this part of the sky, take some other bird, so on. Okay, so my state that I capture eventually should ensure that every bird that was flying is appearing in some picture, and no bird. Okay, so that means I didn't miss any bird. Okay, and no bird should appear in two pictures. Okay, so for example, if a bird is flying from left to right, I take a picture here, it appeared here, and then I point the camera here, it's again appeared in the camera, and you capture it twice. Then you're double counting the bird. Okay? Or the reverse is also true. I take a picture here, bird is going the other way, then I come to the other end, the bird has gone out of field of view, no photo captured. Right? So birds are messages in our example. Okay? So I don't want to lose any messages so that they never get processed. I don't want to process them twice. Okay? And yet, the important part here is I took pictures of the sky at different times. Yet I want to capture a consistent state. My consistent state means I have actually captured the state of the sky, okay, at slightly different times, but I didn't miss anything important. In this case, the important things were birds that I captured. Birds here are messages. Okay? So this is what we want to do with the processes. So now we no longer have a clock. There is no clock, so you don't actually say take snapshot at noon or anything like that. Clocks can be arbitrarily out of sync. We will have processes take their snapshot at different times, just as I took pictures of the sky at different times. But we will ensure that we have taken a consistent snapshot. We did not lose any messages. Neither did we have a scenario where the message gets processed twice. Okay? If you do that, now we got a consistent cut. That is what our distributed snapshot algorithm is going to do. Okay? So we will now do away with using clocks at all because we cannot solve clock synchronization perfectly. So we got to have an algorithm that doesn't depend on it to begin with. Okay. So here's a picture of what is going on. I'll give you the algorithm, and then you can look at an example on the next slide that explains what this is. Okay. So here's the algorithm. Don't look at the slide because it doesn't describe all of that. Okay. So any process, there are n machines or n processes. They're the same in this case. Let's say n processes in your distributed application. Any process can decide it's time to take a snapshot. Okay? It's time to checkpoint state because it's been a while. Okay? So any process can start the algorithm. Okay? The way it's going to start the algorithm is going to pause for momentarily, going to take its memory, okay, and write it out. Okay? The reason you pause is you don't want memory to change while you're writing it out. So you pause, the memory contents are static, you wrote your memory contents. Okay? Okay? Now I saved the memory state, and then you send a message to all the processes with which you have active TCP connections. Okay? Let's say this process has active TCP connection to 2 of the 5 processes in the system, and you will send a message saying start a snapshot. Okay? This is a message we'll call a marker message. A marker message simply means start a snapshot. Okay? And that's it. And then what you will also do what this process will do is for every incoming message, okay, on these TCP/IP channels, you will start saving messages. Okay? Because those are your messages that you will say are in transit. Okay? So you save your locals. When it's time to take a snapshot, save your memory state, send out messages on your active TCP/IP connection, then start a snapshot. Okay? So you are sent on the outgoing side of the TCP/IP channel. Okay? And then you start saving all the messages that are coming into you. Okay? And you will do this until you get a marker message in the reverse direction. Okay? So you send a marker in the forward direction, you start saving messages until a marker comes. When a marker comes to you, you say that's when I stop saving this. Okay? And you just do this recursively at every process, and you get a consistent snapshot. Okay? So the algorithm is very simple. Okay? Convincing yourself that it does a consistent cut is the harder part, not implementing the algorithm. Okay? So let me repeat the algorithm, and I'll actually show you. In this case, here's an example. Here's a process. Okay? So you will see that there is some messages coming in. There are active connections to processes that are the messages are going out. Okay? So here's the process queue. Okay? At any time, it can say you start the snapshot. The way you do this is you pause, you take the memory contents here, you write it to disk. Okay? And then you send out marker messages on these 2 connections. So you'll send a marker message, and then you start saving messages here until you get a marker message in the reverse direction. Okay? And those are the messages you will say are the messages in transit. Okay? And so now, since this process has sent marker messages or start a snapshot to at least 2 other processes, they will recursively do the same thing. Okay? They will first get a marker message on their incoming connection that came from queues. Now think about one of these other processes looks like this. You got a marker message. The marker message says start a snapshot. Okay? So it will pause. It will essentially write its memory contents to disk. Okay? It will send marker messages on outgoing channels. And if there are other incoming channels, there's only one shown here, but there are others, you'll start recording until you get a marker on them. Okay? So this is a recursive algorithm. That's all you do. Each process saves its state. It sends out start a snapshot on its on all TCP/IP connections that are active. It basically starts recording messages on the same channels that are coming in until you get a marker message in the other direction. Is this clear? What I just said? Okay. The question is, how is actually this going to give you anything consistent? Okay, so here are examples of what actually is happening. So in queue's case, you send these marker messages. A, B, and C are actually coming here. So you see that you not only save the memory content, you're saving all of this, and when you stop recording when the marker comes on the incoming channel, so then you're done. So your snapshot consists of memory content and messages A, B, C, and D. Those are your messages in transit. Those were sent after you took the snapshot, but before you sent, because of the consistent nature of the cut, you will have to save them as well. So when you restart this process, you will not only start it from that memory state, you will also insert these messages back into your socket buffer so they can be received and processed again, okay, because they have not been processed. Is the high-level idea clear? We can discuss a little bit why this even works, but yes. Okay, that's a good question. The question is, for the saved messages, if you restart the process, does it matter what time the messages are redelivered? Okay? The answer to that question depends on what kind of computation this is. If this is simply simulations, or let's say it is something like machine learning training, the message the timing of the messages matters less than the contents of the message. Okay? But if those messages are actually the time at which they are received is part of how the message gets processed, then this algorithm does not give you that property, because as you pointed out, the time at which these messages are processed matters. The distance between the time difference between the message might matter, because you didn't save any of that information. You simply saved their contents. You cannot reconstruct it if you restart the process. Okay? So this is only going to work for what we should call batch application, where it's not the timing of the messages as much as the order and the contents of the messages. Right? And so if you have that property, this will work. So for large number of batch job simulations, things like training, that is true, so it will work. But for other things, it may not work. Yes. Can you repeat that? The process what? Okay, that's a good question. The question is, is the process paused until it receives all the markers? So as far as the computation is concerned, you really have to pause while you save the memory state. And then you don't need to, but you still need to continue the algorithm and keep recording the network state. Okay? The memory state can change after you saved it, but the network state you've got to keep recording until the marker message arrives. So you don't have to pause it until all of these things have been saved. You can pause it at step B or resume at step B and then keep saving messages. Yeah, questions, could you send messages? Yes, you will see that you are sending after you did the marker, more messages have gone out. So this process has resumed computation, so it's sending messages, right? So it's not stopped, it is continuing to compute. That's what the example is showing. Is this clear what I just said? Okay. So I think you have to think a little bit to convince yourself why is this consistent, the fact that you are going to actually eventually all processes will stop, that they are not going to recursively keep sending, let's start a snapshot to one another, and this process never stops. So you got to think a little bit. I'll give you an example of two processes and their snapshots, so you can then generalize to more. Okay, so let's say there are processes A and B. Okay, this is a very simple case where there is a active socket connection between the two, right? So process A can start the snapshot and it can say, okay, I'm going to save my memory state, and then it's going to send a marker message which says start a snapshot to B. Okay, and then it started recording on its incoming channel all the messages that are coming, A, B, C, and so on, until a marker message is received. It's now recording on its incoming channel. Okay, so this marker message is going to go and get to B. Okay, at that point, B is going to pause. Okay, it's going to take a snapshot. Okay, so it'll take a snapshot and then it will send a marker on its outgoing connection. That's our rule. Okay, the outgoing connection is the connection that goes back to A in this case. So it will basically send a marker M on this channel. Okay, so basically those messages, so A, B, and C were sent before M, so they will come here. So this process will save all these messages, and then when this marker message comes in, it'll say stop recording. Okay, because the first marker message that you send out says it's time to take a snapshot and you start recording. And when markers come on your incoming channels, you say it's time to stop recording. So when this marker comes in, you stop recording here. Okay. Now, is that clear, what I just said? Now, as far as B is concerned, okay, there's only one incoming channel. Okay, and the first marker message that came, which made it start recording, is the one that's already received. So it doesn't actually have to save any extra messages on its incoming channel. So that message M not only said start recording, it also told you to stop recording, because there are no more messages that are going to come there. And this is the only marker A is going to send it. So B does not actually have to save any messages at all, because as soon as it gets the marker message is saved its state, that is, if that is the only TCP socket that it has opened, then it doesn't have to do anything. It's done. Okay? But if there are other sockets to some other process, let's say C, then it would have to send a message, marker message out and start save those until a marker has come back here. Okay, so not in this simple case, just two processes, you can work this out and figure out how it works. You have a question, there is?
So they're like, after A receives,
Yeah.
or
The question is, I showed an example here where A has started the snapshot algorithm, it saved its memory state, it sent marker messages on outgoing, and it is recording its incoming connections. Okay? And the question is, when does the snapshot occur? So the snapshot is occurring over a period of time. It starts for A, it starts when it saved its memory state, okay? But it continues to record messages until a marker is received. So it ends when you received markers on all your incoming channels. Okay? So it's not a one-time thing. The memory contents are written out, but the recording of channels continues until marker messages are received. That is when it will end for E. The same thing is true for every other process. The first marker message starts the snapshot, okay? And then you start recording, and until you have received markers from all other processes that process communicates with, you keep recording, and then that's when you end the snapshot. Yes, question. Yes. So question is, what will happen if A communicates with B, B communicates with C? You can do the same thing recursively, right? So you can do an example. So this is your example, A, B, and C. Right? A starts the snapshot. It writes its memory state. It sends markers on outgoing channels. So now it has to send two marker messages, one to B and one to C. Okay? And it has to record all incoming messages. So it will start recording all the messages from C, all the messages from B. Okay? These marker messages are going to go to B and C. Okay? When this marker arrives at C, it will do the same thing. When this comes at B, it's going to do the same thing. Okay? And then let's say B does the snapshot first. It's going to send a marker on its outgoing channel. Okay, when C takes the snapshot, it's going to send a marker on its outgoing channel here. Okay, so you just recursively do the same thing. Okay, so it's not going to matter. Each process is simply going to take a snapshot, send markers out, wait for markers to come in. Until then, you continue recording, and that's all you need to do. Yes. A can continue to send messages after you send the marker, but those messages are not going to be stored, right? Anything after the marker, you don't need to care about. Those are not something you will have to worry about. Can A not send the message queue rather than what you send after the marker is not important. What matters is all the messages on an incoming channel until a marker is received. After you send a marker, if you send another message, let's say Z, that is not saved, you don't care, you'll get just processed as a normal message. Right? The question is, will it be lost ultimately? So what you have to do is you're taking snapshots periodically. It doesn't mean every message is logged. So if you're taking snapshots hourly, between those 2 hours, 10,000 messages may be sent or received. You don't care about them. You only care about messages in transit at the time of the snapshot, not messages that are sent afterwards. Okay? Because what will happen is if the process crashes, you'll roll back to this point, restart. Okay? And then all those messages hopefully will get resent because you restarted the computation. So that's what will happen. Yes. Okay. So that's a very good question. So question is, let's say A sent a marker to B, okay, and then B also is going to send a marker to C, right? Because they're all communicating with one another. Okay. So the rule here is the first time you receive a marker, it tells you to start the algorithm. Okay. The second time you receive the marker on any of your channel, that's when you have to stop recording because the first one already started the algorithm. So now this has just become a marker on your incoming channel that's asking you to stop. Is that clear what I'm saying here? Because you will receive markers on all your incoming channel by definition. The first one you process is the one that starts it off. And then you're recording on your incoming. So the B's message in this case is the one that tells you to stop as opposed to restart the algorithm. So you're not going to restart it because that will just be a subsequent marker you receive. Yeah, the question is when you receive a marker from A, do you start saying message from every process? Yes. You have to start saying messages from every process, every TCP/IP connection that's active, because you are going to send markers on those, and then you will have to wait. So all active connections, you have to start saying this, right? So those are all your messages in transit. Okay. Any other questions here? Okay, so we had quite a bit of explanation. I think you can go and draw some simple examples. I think once you draw it, you understand the algorithm. It's not very hard to understand. I didn't give you a proof of why it works, but you kind of have intuition, hopefully. Okay, so we are kind of out of time, so maybe we just stop here, okay, and end it here today. As I announced last time, okay, as far as the midterm is concerned, which is going to be happening after spring break, everything I covered until today is going to be on the midterm. Okay, what I do on Monday and Wednesday of the week after for the final, not on the midterm. Okay, lectures 1 through 12, which is today's lecture, you should make sure that you review for the midterm. I will very soon put out a sample exam, so you can see what kind of questions to expect. I will also add some more practice questions that go beyond the sample exam, so you can do a little bit of practice to get prepared. Okay? But the more important thing is, between now and next Thursday, from 2 weeks from today, okay, use your time well to prepare for the exam. We are available if you have questions about any of the material, okay, that we have covered for all the 12 lectures. Ask us questions. We're happy to tell you whatever you need to know. Okay, so we'll end it here. Have a good break. Okay, we'll see you Monday after spring break.